The hardest part of building a bridge over deep water is not the span everybody photographs. It is the part nobody ever sees, built underwater in the dark, in a current, on ground the engineers can only guess at until they touch it. Every bridge over water starts with a question. What is down there? Long before anything is built, survey vessels map the riverbed or the seabed with sonar, and drilling rigs on barges punch boreholes down through the mud and sand until they hit something that can carry a load. Sometimes that is rock at 15 meters. Sometimes it is soft sediment for 80 meters, and the rock is somewhere further down still. That single answer shapes everything that follows, because a bridge foundation has to reach material strong enough to hold up thousands of tons without settling. Engineers also need the current speed, the tidal range, the depth of scour, and the history of how the channel has shifted. Rivers move. A pier that sits safely in slack water today can be sitting in the main current in 50 years' time, and scour, the way flowing water digs the bed out from around an obstruction, is one of the most common causes of bridge failure in the world. In shallow water, the classic answer is a cofferdam, and the idea is beautifully simple. You build a wall around the spot where the pier will stand, then you pump the water out from inside it. Interlocking steel sheet piles are driven down into the bed with a vibratory hammer, forming a continuous watertight box. Once the ring is closed, pumps empty it, and suddenly there is a dry hole in the middle of a river. Crews climb down and work on the bed as though they were on land, digging out soft material, tying reinforcement, and pouring the pier base in the open air. The pressure trying to collapse that box is enormous, so the walls are braced with steel frames as the water level drops. Often a plug of concrete is poured underwater across the bottom first, and only then is the water pumped out, so the plug resists the upward pressure of groundwater trying to lift the whole floor. Cofferdams are cheap and well understood, but they have a limit. Push them into deep water or fast current and the forces and the cost climb very quickly. For deep water, engineers use a caisson, which is essentially a giant hollow box or cylinder that becomes part of the finished foundation. The caisson is built at a yard, floated out like a ship, positioned exactly and then deliberately sunk. As it descends, workers or machines excavate the soil from inside it, and the caisson sinks under its own enormous weight, cutting down through the bed until it reaches load-bearing ground. Then it is filled with concrete. The most famous version of this is the pneumatic caisson, used to build the Brooklyn Bridge in the 1870s. Compressed air was pumped in to hold the water out, and men dug at the riverbed at the bottom of the box in a pressurized chamber. It worked, and it also nearly killed the project's chief engineer. Coming up too fast from that pressure caused decompression sickness, which they called caisson disease and which we now call the bends. Modern caissons are usually excavated by remote machinery precisely so that nobody has to be down there at all. The third method, and by far the most common today, is piling. Instead of making a dry space, you drive long steel tubes or concrete columns down through the water and the soft bed until they bite into strong material far below. A pile-driving barge holds the pile vertical while a hydraulic hammer strikes it thousands of times, driving it down by centimeters a blow. In deep water and difficult ground, engineers use drilled shafts instead, boring a hole down through the bed inside a temporary steel casing, filling it with a heavy fluid to keep the walls from collapsing, then lowering in a steel cage and pumping concrete from the bottom up so it displaces the fluid rather than mixing with it. On a big crossing there may be dozens of piles under each pier, tied together at the top by a massive concrete slab called a pile cap. The cap spreads the weight of the pier across the whole group, so no single pile carries the tower alone. With the foundation in place, the pier grows out of the water, usually as a hollow reinforced concrete shaft cast in place using climbing formwork that jacks itself upward a few meters at a time. Then comes the deck, and here the water works in the engineer's favor. Enormous prefabricated deck sections can be built on shore, floated out on barges, and lifted into place, which is far easier than assembling them piece by piece over open water. On long crossings, engineers often use the balanced-cantilever method, building the deck out from each pier in matching segments on both sides at once, so the half-finished structure stays balanced on its own pier like a seesaw and needs no support from the water below. Every segment is stressed together with steel tendons under enormous tension. Elsewhere, launching gantries crawl along the completed deck, picking up segments and placing them ahead of themselves. The last segment, where two arms meet in mid-air, is the tense moment of the whole project, and it is usually placed at night or early morning, because a steel deck expands and contracts by centimeters as the sun heats it. The whole time, the sea is trying to take it apart. Salt water drives chloride into concrete, which attacks the steel reinforcement inside and makes it rust, and rusting steel expands and cracks the concrete off from within. So marine bridges use dense low-permeability concrete, thick cover over the steel, epoxy-coated or stainless reinforcement, and sometimes an electrical current run through the structure to stop the corrosion reaction. The splash zone, the band that is alternately wet and dry, is the worst place of all and gets the most protection. Below it, divers and remote vehicles inspect the piers for scour every few years, and where the bed is washing away, engineers dump rock armor around the base to protect it, which is why the cost of a major water crossing is measured in billions, and why the piers, not the span, are almost always the schedule. Follow for more construction facts hiding in plain sight.